Today, we're going to be talking about something that's pretty hot right now. We're going to be diving into the world of MLOps.
Oh, yeah.
And
It's
specifically,
a good one.
we're going to be looking at professional certifications
Yeah.
in this field.
Nice.
Yeah.
MLOps is,
If you're out there and you're thinking about maybe getting a certification in this space,
yeah.
this is the episode for you because we're going to be talking all about what it could mean for your career.
Okay, so now let's get started. So first few sessions will be theoretical and after that we'll move into the practical as well. Okay, so Linux kernel. What is Linux kernel? So today we are going to discuss about the Linux kernel internal. So this session will be basically kernel is very important for your interview purpose because most of the organizations in the MLOps they keep the 20% of the questions in the kernel actually. So they'll ask you Linux kernel, Linux commands, and Linux related questions and all. So that is very important troubleshooting skills and all. So Linux kernel internal. So what is kernel? So basically kernel is a computer program. We all know that. It's nothing great about it. So it's just a program is written in C at the core of computer operating system and generally has a control over everything in the system. That means kernel controls everything in the system and it's a computer program. So now if you see that we have a hardware layer, on top of that you have a kernel, and then on top of the kernel you run all the user specific application like MS Office, browser, notepad and all kind of things. So this is something which you have. Now the question is where kernel programs run. That is important. So kernels is basically is a kind of very small code which is a portion of operating system code that is always resident in the memory. That means the moment you start your computer, that code is always running in the memory, and that code itself facilitate the interaction between the hardware, which is CPU, RAM and hard disk, and then software which you are using like a browser, notepad and all kind of things. So this is resident in the memory. Now next question is where the kernel program runs. So the kernel is one of the first program loaded on startup after the boot loaded. So when you when you start your laptop or some machines, then first bootloader get loaded, and after that bootloader, the kernel load in the memory. That is the things. Now what are the types of kernel we have? So we have multiple different types of kernel: microkernels, monolithic kernels, hybrid kernels, nano kernels, exokernels. So all these types of kernels which you have. Let me ask you one thing. Do you know that your Android is also Linux kernel? The mobile, if you have Android mobile, that is also Linux kernel. Have you, do you know that?
Yeah, yes, yes.
Yeah, so that is thing. Now the next question is what are the primary role of the kernel? So primary role of the kernel which include task management. Task management means whatever you see here, right? This is the task manager. So whatever the task is running in your operating system, that all is managed by kernel. So each task you see that you get a PID and some username is required for running these applications, CPU, memories and all kind of things. So this all is done by kernel, and sync and communication is done by kernel. Memory management, which task should receive what, how much memory, how much RAM and all, that is also managed by kernel. Timer management, interrupt and error handling, and device input and output also. That means when you send any request to the computer through keyboard or mouse or maybe printer or whatever it is, so input output all these thing managed by kernel. So yes, the full kernel control all hardware resources, example input output, memory, cryptography, where device driver arbitrates conflict between the processes concerning such as resources and optimize the utilizations such as CPU, file system, network socket, memory management, peripheral and devices, input output and many more. So this is something which you have. Do you know who's this guy? Any idea?
Rajesh, just a minute. Just I would like to ask you that this deck will be shared with us, right? So we
Yeah,
don't
yeah.
have to take one. Okay.
No, no,
Okay.
everything will be shared. You just need to
Okay.
focus on the session. And if you have a
Okay.
doubts, you can ask me. I'll share the recordings, all the tutorial step by step, slides, everything, sample programs, everything I'll share throughout the session.
Okay. Thank you. Thank you.
Okay, so any idea who's this guy?
I don't remember his name, but he's the one who actually created Linux,
Yeah.
like
So his name is Linus Torvald. He's the
Linus. Yeah.
yeah, Linus Torvald. He is the father of Linux, and same time he is the father of Git also. Mind it, Git, the one which I'm going to teach you next week. So it's his product only. So yeah, Linux kernel is a free and open source. It's a monolithic, modular, multitasking, and Unix-like operating system kernel. It was originally authored in 1991 by Linus Torvald for his i386 based PC, and soon adopted as a kernel for GNU operating system. So which was written to be free library replacement for the Unix. Now, use of Linux kernel, more or less, we understand that. So nowadays, if you see that any devices is coming with the kernel, some sort of kernel of Linux only. You talk about IoT, you talk about the MLOps, you talk about the AI ops, you talk about the robotics, you talk about the, this quantum technologies. Everywhere is Linux kernel only. So you have to be pro in that. Again, we are getting to going, you have to go to the basics and learn all this stuff, because new technology required the expertise in each or this thing. So yeah, Linux to deploy in a wide variety of computing system, such as embedded devices, mobile devices, personal computing, servers, mainframe, and supercomputers. Okay, so now the next question, this is a very important one. They'll ask you what is a bootloader, and this is something you have to understand that. So bootloader again is a very minimal program. Okay, very small program. Now when you switch on the power button, okay, so this bootloader is embedded in your motherboard itself. This is a program embedded in the motherboard, and the moment you switch on, that this bootloader get run in the motherboard, I mean the kind of ROM. So bootloader is also spelled as a bootloader or boot manager, and a bootstrap loader is a computer program that is responsible for booting a computer. So you see the bias and all, you get it right. So because of the bootloader only. So how bootloader works? So when a computer is turned off, is software including operating system, application code, and data remains stored on a non-volatile memory. Non-volatile memory means the one something hard disk. Okay, so if you want that certain programs to be loaded in a memory, volatile memory, that means RAM and all, then you have to use the bootloader. So when the computer is powered on, it typically does not have an operating system, or it's loaded in a random access memory, RAM you call it in short. The computer first execute relatively simple program stored in the read-only memory, and later EEPROM, NOR flash, and stuff like that, along with the some needed data to initialize RAM, especially x86 system. So your system, the laptop which you're using, or the VMs which you'll create, you are using nothing but a x86 system only. Remember that. That's the architecture of it. To access the non-volatile device, usually block device, example NAND flash and stuff like that. So yeah, operating system program and data can be loaded into RAM with the help of bootloader. So look at this, the flow. When you power on, ROM code get introduced, which load the boot devices, and then bootloader load the kernel, and then you get the platform. So this is the workflow. So yeah, powered on, load bootloader in ROM, load kernel in RAM. Did you understand that, all of you?
Yes.
Oh, yeah, one question, Rajesh. Actually, this bootloader resides in ROM itself, is it?
So bootloader resides in a motherboard, and
Uh-huh.
when you start the motherboard, I mean switch on the computer, so that it get loaded in ROM. ROM means random access memory, which is a part
Okay,
of the
okay.
motherboard only. And then motherboard you have a RAM where the kernel runs actually.
Okay.
So little bit of memory you have in a motherboard actually. Little
Yeah,
bit of
okay,
memory.
okay.
Okay, so now this is a little complicated. You don't need to know, but yeah, if you have interest to get into that deep dive, that you can go into that. So look at the process for booting all this in application level. So here, now this image is very important. Primarily, I want you to focus on it. Look at this from the step number 1 to second to third to fourth and fifth. So first thing, what happened? Sock ROM bootloader get introduced, loaded. Then first stage bootloader, and then second stage bootloader. What is the difference between first and second? At a high level, you need to understand nothing. You have to take it seriously at this level. But if you see that bootloader runs in the space which is called bootloader space. Left side you see bootloader space. Okay, now after the bootloader, you call the devices, I mean storage. Basically in storage you have kernel. So that Linux kernel device file get loaded in your RAM. Okay, and if you see that where the kernel runs in the kernel space. Left side you see kernel space. That means here you have three space: bootloader space, kernel space, and the user space. And here you see fifth one, which is all the root file system. Root file system means what? I want to know root file system. So here this is something get loaded in the user space. Root file system, enter, and click on this. And I'm sure you must have seen these images, right? I mean, this every day when we work on the Linux, this is called root file system. So whatever the file system you see in the root, that is a part of the root file system. And the root file system get loaded in which space of memory? User space. So here overall memory is divided into the bootloader memories, virtual memory, kernel memories, and user memory. And then these are the things which happens. Are you understanding, all of you?
Yes. So
So
you're
remember
So
saying
the
that,
that
RAM
what
is divided into these three spaces, right?
yeah, one by one. Yeah, please go
Yeah,
ahead.
I mean to ask, the RAM is divided like these three spaces.
Yeah, no, bootloader works in the ROM. Okay, here you see ROM, but this
Okay.
kernel space and user space runs in the RAM. And RAM,
Okay.
first program which get loaded is kernel, and kernel after the loading a kernel, then is running in the RAM, and then after that root file system get loaded. Root file system is your C drive, D drive. Just now I showed you in the Linux one, right? So
Yeah,
these are the
yeah,
things.
yeah. Okay.
So that is this thing. So remember that it's a user space, kernel space. This two is virtual memory, which you divided into two part, and bootloader is RAM, ROM, basically.
Okay.
Okay, so what is
Yeah.
the difference between kernel space and user space? So this is very important question, okay? Because they will ask you every interview questions, like if you're trying the farm company and all. So every company they'll ask you this question: what is the what are the space? How do we divide the virtual memory? So you should say yes, a virtual memory of your laptop divided into two part basically. Laptop means your compute unit divided into two part. One is kernel space and the another one is virtual space. So now they'll ask you difference and what exactly kernel space, what exactly user space, how the programs talk from the user space to kernel space, all these things they'll ask you. So user space and kernel space, yeah. So computer OS originally segregate virtual memory into user space and kernel space, mind it. So all the memories of the computer is into divided into two part: user space and kernel space. So now what is a kernel space? So kernel perform a task such as running processes, managing hardware devices. We discussed initially also. Same thing, kernel you know that what it runs. Kernel performs tasks such as running processes, managing hardware devices such as hard disk, handling interrupt in the protected area called kernel space. That means here kernel space is a protected area. Whereas in contrast, any application you run, mind it, any application you means user runs, that is running in the user space. What applications? Such as browser, word processor, some audio, video, whatever you run, that runs in the virtual memory area of user space. That means you run application, it run in the virtual memory of user space. When kernel runs in the kernel space. So kernel space is a protected area. Okay, are you getting the point, all of you?
Yes, yes,
Yes.
Rajesh.
Yeah, so that is how it is. So yes, uh, just a second, let me go through this. Yeah. So now why kernel user space and why kernel have user space and kernel space. So primarily what is happening, uh, this separation serve to provide memory protection and hardware protection. What happens, user can run any kind of application. So now if you're running all the application which is a kernel and user, what will happen, you will run some bad applications and which will destroy the kernel, and then kernel is destroy, your operating system gets stopped, correct now. So that is the reason what is what operating system are doing, they are running the kernel in the one area which is called kernel space, and they're running all the users application user space. That is the why, to protect the kernel and hardware, okay, to from some hacking or something like that. So this separation prevent user data and kernel data from interfering each other and causing instability and slowness, as well as preventing malfunction application from affecting other application or crashing the entire operating system. So that means users are allowed to run application in user space. Kernel space is running the kernel application. Why? So kernel space is protected. You cannot run in the kernel space. So because of you want to protect the kernel and operating system and hardware, so you this design is introduced. So now it's very clear, user space, that means all the virtual memory of your laptop, I mean compute unit, not laptop, is divided into two parts, user space and kernel space. Now kernel runs in a supervisor mode and has access to user section as well. That is important. See, kernel is running in the kernel space, but also kernel runs in the supervisor mode. That means kernel can access all the users application, but users cannot access the kernel. Okay. Kernel space, user application cannot access this one. So here you see that user space application run in user mode with limited privileges, and each application has its own virtual memory map. So please remember that. So here again, kernel runs in the supervisor mode and has access to user sections as well. The kernel's memory map is fixed, whereas application runs in the user mode with limited privileges. Each application has its own virtual memory map. So you see that supervisor mode and user mode, kernel space, user space. Are you understanding?
Yeah.
Yes.
So now this is the most important question. They will ask you, okay, tell me, because user has a limited access and user need uh, all the capabilities like CPU, RAM, input output, hardware, all these things they run it, and everything is done by kernel. So how this application running in the user space, if they need a hardware resources or software resources or whatever it is, how they request the kernel, because without a kernel, because kernel space manage the hardware, right? So if they need a hardware, how did they request? So this answer you should give system call. Okay, that means a process running in the user space make a call to kernel space for requesting, hey, give me this one, give me that one, and that process is called system call. Okay, this is important question. So system call, and then that is how the all the resources being allocated. So here you see system call is a library basically, okay, and it has a multiple method. For example, let's say one application you want to run, so you want to PID for that application. You see that every application you have a PID. Look at it here. Here, PID. So you have to ask a PID from the kernel. So get PID is one function which is making a system call, and here kernel space you have all the resources like a PID namespaces, UID, network, NFS, XFX, block, everything you have it, and they ask the resources through the system call and then get it. So this is important. Please understand that. So you have a hardware on top of your kernel which manage the system interface, generic services, device driver, and then top of the user space. And this is the summary of it. Are you understanding, all of you?
Once can you repeat the last line? So using system calls, it will happen. That's what you're saying.
Yeah. So if we'll ask you, hey, how this application running in the user space talk to the kernel space, you should answer system call. System call is one of the interface using that user running in a user space ask for the resources from the kernel space. Come in kernel basically. Got it?
Oh, okay. Oh, got it.
Yeah. So this is the different method and stuff like that. Okay, so now this is just a summary, good image, I got it. So here Linux kernel has millions lines of code which can help you to read and write files, decide which program get to use it, the CPU, and then make a keyword work in a short. Now when Linux kernel run, that's called when Linux kernel code runs, that's called kernel space. When your program runs, that's your user space,
User
right?
space.
Yeah. So now there's a context switching. I'll discuss about it right now. I'm not discussing, and so on. So now you see that hardware, then kernel space, which talk system calls, file
Just a
system.
minute. Did you explain get PID and that process like
So
you
these are
have showed in?
so system call is an interface. In the interface, there's hundreds of functions like that. So example of functions like a get PID, open files, close files, exit, all these things are functions. So you don't need to remember that one. Hundreds of functions are
Oh,
there. Okay.
okay.
Uh, yeah. So system call has a hundreds of functions. There's a two functions just for example. I show you. Okay. So this is the
Oh,
way. Let's move on. So this is a complete detail. This image has been taken from the wiki. Again, just for understanding purpose, if you want to get it, you can see that these are the function. You see start, splash, dump, read, open, ictl. A lot of functions we have. See about 380 system calls are there. This means 380 method you have where the user space make a use of this system call method and then make a process scheduling, IPC, memory management, virtual files, network file systems, and all stuff like that. Got it? Yeah.
yes, yes.
Okay. So, yeah. So this image we have studied in our colleges also, right? So you see that you have a hardware on top of kernel, then top of shell, then you have a user. So you interact with the shell talk to the kernel talk to the hardware, and get all this thing done. So your application is running around all this thing. So yeah, look at this very good image. So here you have a kernel in a kernel space and then user space, and kernel's user space, all the applications is making call to the kernel using system call interface. Okay, so that is important. Again, same image in a different picturizations and so on. So now you understood the system call is very important. In computing, a system call, also known as syscall, is the programmatic way in which a computer program requests a service from the operating system on which it is executed. Okay, so this may include hardware related service, accessing the hard disk drive or accessing the device cameras, creation and execution of new processes, and communication with integral kernel services such as process scheduling and so on. So that means system call provide an essential interface between the process and operating systems. Mind it, in most systems, system call can be made from user space processes only. Okay, so this is something which you have. So now you understood the system call, you will not stuck, right?
Yeah.
Yeah. So
Yes,
I must
yes.
tell, system call is a very important question. Every interview they ask if they are talking about the Linux kernel. So system call provides services of the operating system to the user program via API. Now it provides the interface between the process and operating system to allow user level process to request services of operating system. System calls are the only entry point to the into the kernel. Mind it, system call is the only entry point into the kernel system. So what exactly you can do that? So same function of the kernel, which you can call it process creation and management, system call. Main memory management, system call. If you want to access the file, system call. You want to access the directory, file system management and all, system call. You want to send some request, system call. You want to get something from the system call. Protection related, networking related, everything is being done by system call. So this is the one. So now again, these are the types of system call which just now I discussed and so on. So how system call works? So basically you don't have to dive into that. Basically there are two ways where the make API call is being made. Okay, and this is something which you can, at a high level, you understand that how the system call works. So the kernel, Linux kernel provides several interfaces to user space application that are used for different purposes that have a different properties by design. So there are two types of application API basically in the Linux kernel that are not to be confused with. So here we call it this API. One type of API we call it a kernel user space API, and there is another kind of API which is called kernel internal API. So two API, using that you make a call from the users to kernel space and get the resources done. So this is all the explanations. I'll just ignore it because this will be too deep dive into that. Okay, so yeah, yeah, just this is the concluding message. Just spend few seconds on it. Just a second. Just a second. Yeah. So Linux kernel has code to do a lots of things. Read from a hard drive, make network connections, create a new process, kill process, change file permissions, keyword driver. The program does not know how to do the things like a TCP dude. I have no idea how it works. No, I do not know how ext4 file system is implemented. I just want to read some files. That is where that here you have program ask Linux to do work for them using the system calls. So please write to this file program, switch to the running kernel code. Done. I wrote this code and then it's done. So anything, if you ask, every program uses system calls, and every system calls has a number, example, some permissions and all kind of things. You can see which system calls is a program is using with this strace. So strace is a command. When you run it, you will see that which system call is being used. So when you, let's say you want to list out the file in a TMP, so lstmp, and just try with strace, will show you every system call uh, ls uses. It's really fun and so on. So this is the one of the wonderful commands which you can get it done. All of you understanding this?
So strace is the command for tracing the system calls,
To
whether
understand
it's
that which
a
system is, which system call is working actually.
so it be used in user space as well as internal space of the kernel. So both
Right,
of
yeah,
them, right?
yeah, yeah.
Okay.
Okay, so are you understanding, all of you?
Yeah.
So
Yes. Yeah.
they will ask you, how do I know which system call I'm using? So you say like there are 100, more than 300 system calls are there, sys calls are there, and the easiest way to know that is to strace and then the command which you will make it. Easiest way to do that. Got it?
Yes.
Yeah. Okay, so these are the some sample, only example of sample system call. There's so many system calls are there. Okay, so process control, these are the one. File manipulation, these are the one. Device manipulation, these are the one. Information maintenance, communication, and production. So these are the one which you have now. System call. Okay, so this is a specific to the process. These are the different stages of process creation: new, ready, waiting, running, and terminated. Same thing. And I'm just ignoring it because we don't want to get into the method, which you don't need to know, because it'll become too much for grasping it. So I'm avoiding few things and done. Now this is important questions. Next one is process and threads. Okay, so what is a process and thread? So here you see that here you have a process, and process have a multiple thread. So here you see CPU get allocated to process in this image. CPU get allocated to the process, and process you have a multiple thread 1, 2, 3, and so on. So the question is, what is process? So you know, everything in the computer which is running is a process. If it's running, it is a process, right? So process is a computer program under executions. That means running. Linux is running many processes at a given time, and we can monitor them on the terminal using the ps command. That means if you run this ps command, you can get it. PS command or on the system monitoring UI. Linux processes are isolated and do not interrupt each other. That means each processes, now they'll say, okay, what is a process? A process is created, understand that. Each program you want to run, it required a process. It is a process. Now this process required the CPU and RAM, so they'll get it from the kernel using the syscall, right? Now each process are running independently. They are not interrupting each other. Okay, so that is important one. Now what happens, because you are running so many processes. Now let me show you how many processes I'm running. See, there are so many processes I'm running in the Windows machine. See, these all are process, and each process is identify the unique ID number, which is called PID number. So this is something which you have. So here process, with the PID, we can identify any process in Linux. Okay, internally the Linux in the kernel uniquely allocate this number and release it for the use after the process exit. Since many processes are running at any given time in Linux, they have to share the CPU. Understand that? See, each, I want you to look at this one very carefully. Okay, so see here, there's so many processes running, and each of these processes are consuming so much of memory. You see, this one is memory. The hover, you can see my cursor, right? Hello?
Yes, Rajesh, we could see.
Yeah. So you can see that all this memory
Yes.
utilization. But if you look at the CPU table, do you see everywhere is 0, 0, 0, 0, 0, 0? And only here you see one or two process which is having the CPU. See, one or two max. So what is happening? So for running, understand that for running the process, you need a memory. Okay, but for using that application or process, you need a CPU. CPU is basically you need for using that. Okay, so when you need a CPU, so one process to another process, you see that if you see carefully, this sometime it's switching, you know, each and everything is switching. Right now it's very slow, but in real time it is switching very fast. You won't have any, you cannot measure in a millisecond also, nanosecond also. It's very fast. Okay, so it's switching one program to another program. And GoToMeeting I'm right now running using your see my screen. So right now you see that all this thing either system idle and then GoToMeeting system idle, and then interrupts also there, and some in between some antivirus or this that and all kind of things. Correct. So here what is happening, you need CPU to run the process. Correct. So the now that when the one process switches to another process for the CPU allocation, that that process is called process context switching. Okay, okay, are you comfortable? So since many processes are running at any given time in Linux, they have to share the CPU, and the process of switching between the two executing process on the CPU called process context switching. Context switching is important one. Will you remember that?
Yes.
Yes, Rajesh, but you said that memory allocation is somewhere 0K, right? In that case, CPU has not yet started running, it means.
No, no, no. For running any
Hmm.
application, this I'm showing you all the application required the memory. That's the reason you see
Okay.
every process you have a memory. You see 400, 4000,
But somewhere
45,000.
you showed 0K, right? There was no memory allocated for that.
No, no, no. every process which is running required certain memories, okay, to hold that.
Hmm.
But here you see, I'll show you this. Look at this. Here you see, this is the memory allocation, this is CPU allocation. Now you see, every process you have memory, every process you have ID, every process you have users running with a certain users. But now only I'm talking, look at this here and look at this here. This all process I'm not using it. It's running, but it's not I'm using it. So CPU allocation
Okay.
is 0. But here if you see, go to
Okay.
meeting, I'm using it. Go to meeting, I'm using it. So here the context switching is happening. First CPU will be transferred to here, then here to here, again this will here, then again here. Now this is, I'm explaining very slow, but it will be happening very, very fast in real time. So you will not realize that which application which never got the CPU, because it's happening
Okay.
so
Okay.
fast. So this process of switching the context is called process context switching. That's what I'm talking about. Got it?
Okay. Yeah.
Yeah. So process context switching is very expensive actually. What happens? See, you are using Chrome. Understand that. You are using Chrome and then you are using WordPad, MS Word. So now when CPU is taken away from the word, then they have to store your data, correct? Others should not be lost, right? Correct now? And same time, if you're browsing something, so your compute unit has to store all the browser sessions you have activated and then move to the WordPad. So this process is very expensive. That's what I'm saying. So process context switching is expensive. Why? Because take time and also it consume lots of memories for it. Okay, so process context switching is expensive because the kernel has to save old registers and load current register for the next application, memory map and other resources. So that is taking little time and also it is consuming your resources. Are you getting it? Last point.
Yes.
Yeah, so see here, when you move to here and here to here, so he has to store this state of the application, otherwise you lose the data, correct? So this migration for that, for first store, then move, this takes time plus resources also. That is what I'm trying. So now the question is, how do we work with it? How do we avoid this expensive work from the switching the CPU from one process to another process? And that is where we have a concept called threading. Okay, so the solution, the problem which is introduced by the process, which is isolated, each process are isolated running independently, that is introduced by threading. So you might have seen that multiple threads we have for the process. So here, what is a thread? So thread is also lightweight process, but a process can do more than one unit of work concurrently by creating one or more thread. That means when you have a process and that process have a multiple thread, so here what happened, the because it's a thread, you don't have to switch the one process to another process. That way you save the resources and time for it. Okay, so that's the reason people are developing an application which is having one process but multi-threaded application. Why? Because that way the application is very fast basically. Okay, so yeah, thread is a lightweight process. A process can do more than one unit of work concurrently by creating one or more threads. These threads are being lightweight, can be spawned quickly, and also you can also run this command ps-elf to find out. So here if you see, I'm running this command ps-elf and see here, these are the number of process you see, lwp you see. So this is the process ID 11 and how many you have, number of LWP means number of thread, how many you have. So these are the 1111, but if you go down here, see 8 thread you have in this. So this process you have 8 thread. You see Apache exporter running with 8 thread, 1 2 3 4 5 6 7 8. You see these all are belong to the only one process, which is, see that process 1826 and all this thing is having the one thread. See. Okay, so what happens when you have a threaded applications? So threaded applications process context switching cost is reduced and it is much faster approach. So let's see an example. Identify the process and thread in Linux using this command and all this thing which I showed you, and then you can see that number of thread. So Did you understand that process? What is process? What is the thread? All of you?
Yeah, yeah.
Yes.
So it's multi-threaded in the sense that all will be executed in parallel, is it?
Hmm. Yeah.
Okay.
Okay. So this is the thread. So yeah, single thread process. Any thread created within a process share the same memory. That is important. Any thread created within a process share the same memory and resources of the process. In a single threaded process, the process and thread are the same as there are only one thing happening. We can also validate ps-elf output from the previous discussion that PID and LWT are the same and single threaded process. Now, multi-threaded process. In a multi-threaded process, the process has more than one thread, such as a process accomplishes multiple tasks simultaneously or at almost all the same time. As we know, the threads share the same address space of this process. Therefore, spawning a new thread within a process become cheaper in terms of the system resources compared to starting a new process. So thread also can switch faster since they have a shared address spaces with the process compared to the process in the CPU internally. The process has only a stake in the memory and they share the heap and tap tap tap. So that means that's the reason we have a multi-threaded process, and this is something which we do that. So yeah, what is the difference between process and thread? So this slides will help you. So process, if they ask you, then you say is process is a heavyweight, thread is a lightweight process, also called an LWP. Okay, lightweight process, LWP, lightweight process. Process it has its own memory, but thread share the memory with the parent process. Okay, another thread within the process. Process inter-process communication is slower. That means because CPU assignment, inter-process communication is slower due to isolated memory. In the thread, inter-thread communication is faster due to shared memory. Process context switching between the process is expensive due to saving old and loading new process memory and stack info. Thread context switching between the thread is less expensive due to shared memory and all. So when you get these questions, will you be able to answer, right?
Yeah, Rajesh, but if one process is having one single thread, in that case, that only it's a heavyweight, lightweight. That is the advantage
Have
we
it.
have.
Yeah, yeah.
So,
That means see CPU allocations which has to happen. So CPU allocation has happened at the process level. So whatever the CPU allocated to the process, all the threads uses. So if you have one thread, then again other process will run, then again it will do only one thing. One process, one thread means it will do only one thing. But one process,
yeah,
multiple thread, that means it will do multiple thing with the same CPU. So context
yeah.
switching cost will be reduced actually. That means your system will be faster, do more things actually.
Okay, one process, so one single thread is not going to do much for us. There is not
Right,
much of advantage of it. Yeah.
right. Yeah, so this is some of the questions related to uh, Linux internal scheduling and preemption. This is a conceptual thing. So here just understand the scheduler or process scheduler. So Linux kernel controls the way the task or processes are managed on the system. The task scheduler, sometimes called process scheduler also, is a part of kernel that decide which task to run next. Okay. So who's deciding which task to run next? Right now it was switching right here. You see that it was switching from one to another, another to one. See the CPU? See that here switching. So who will decide? So this is decided by process scheduler basically. which is responsible for best using the resources to guarantee that multiple tasks are being executed simultaneously. This makes it core component of any multitasking operating system. So yeah, this is a scheduler.
So inside this process scheduler, it will contain multiple threads, right? So thereupon it will overcome its heavyweight, like lightweight, heavyweight. You explain the difference,
No, so the
right?
process is basically any application you run and allocate the virtual memory. That's a process. Now, if you are running process under execution, that means that requires CPU. So that you may be using some more application running in the background, which required also CPU. So whether which application should run now and get allocated to the CPU, who will decide? So that will be decided by Linux scheduler, aka process scheduler.
Then how where it comes with heavy weight and lightweight? How
So
it
see here,
comes?
what is happening? Understand this way. So right now we have a two process, one, two, three, four. Now who should get the CPU? So this is decided by process scheduler. Okay, depends on
Okay.
their synchronization and use.
Okay,
Now
just like
that's
round
called
robin algorithm.
multitasking.
Oh,
Now
yeah.
each process, let's say this process you have a five thread. That means you can do five things together at a time. When same CPU you
Hmm.
can get it five things you can do. But let's say this process you have only one thread. That means CPU allocation happened and you can got only one thing. That means to get another thing you have to come back again in the process context switching, and then scheduler will schedule that work. So this will get little slower. This will get more faster. Correct.
Oh, so in that context, you're saying that it is lightweight and heavyweight. So when we
Right.
use threads, at a time we can execute multiple tasks without waiting for one task to complete.
Correct.
But when it
Yes.
comes to a process, one after the other, so that's the reason you're saying it's a heavyweight. That's
Yeah.
it.
Yeah. Yeah. So this is the process scheduler. Preemptions. What is the preemption concept? So preemption concept, basically the theory behind is task scheduling is very simple. The theory behind task scheduling is very simple. If there are runnable process in the system, at least one process always must be running. See, if the system is running, at least one process must be always running. So which process? So that's called process PID1. Let me show you here. See that PID1. This system is running as long as this is running. Okay. This is PID1, first process. Okay. So in Linux also, let me show you here. This is the fourth. This is the my system will be running Windows as long as this is running NT kernel and system. Okay. So now behind the task. So if there are runnable process in the task, at least one process must always be running. If there are some runnable process than processes in a system, not all processes can be running all the time. Therefore, some process need to be stopped temporarily or suspended. Okay, so here understand that if there are more runnable process than processes in a system, processes means see 2 CPU, 4 CPU, 5 CPU, multiple processes are there. So if what I'm saying, if they are more runnable process, which you need demand is high, but processes are less, then not all process can be running at a time. Correct now? Let's say you have a 2 CPU. You cannot run 10 at a time, 10 process at a time. Correct now? You cannot allocate 10 CPU at a time. So what to do? So that is where that therefore some process need to be stopped temporarily or paused or suspended so the other process can be running again. So that work is decided by the queue concept. So the scheduler decide what process in.
Sir, yeah.
Yeah.
Sir, for threads, CPU won't be allocated, sir. It will be that threads will be executed on a single CPU.
Yes. So here each process we get a CPU allocation. Now this CPU will
Uh,
be shared between the thread. Okay, there
uh,
thread. So that is the reason all this work can be done at a time.
okay, but when it comes to process, individually CPUs will be allocated. So that's the
Yes,
reason which has priority that will be allocated. Okay.
right. So here what is happening? Preemption is a concept basically. So what happens? You have a too many processes to run, but you have a many less processors. So what happens? Some processes to be suspended or temporarily stopped. So what to do? So in this case, what happened? Scheduler decide what process in queue will run next. That is, you know that. And as already mentioned, Linux, like all other Unix variant, is a multitasking operating system. That means several tasks can be running at the same time. Linux provides so-called option called primitive multitasking, where a scheduler decide when a process is suspended. That means as part of making this process multitasking, there is a primitive is there which decide which helps the scheduler to decide when the process is suspended, and this forced suspension is called preemption. That means if your system is running multitasking and want to prioritize which process to run, which process to not to run, so something which you want to suspend the program, that process is called, that forced suspension of the process is called preemption. All Unix flavor have been providing primitive multitasking since the beginning. So this is the last concept of the in Linux internal. There are few more things also there, like concurrency. Like a concurrency is the execution of multiple instruction sequence at the same time, and sync for all these processes and so on. Okay, so this is the Linux internal which you have to understood and then practice. All of you understood now?